Good afternoon. My name is Fabio Gonzalez, and I'll be presenting the Chapter 9 overview alongside my partner Donovan. So starting with explaining the properties of gases using the kinetic molecular theory, let's explain why gases are so compressible and have such low densities. So the kinetic molecular theory states that individual gases have negligible volume. This also means that there's mostly space between the gas particles. Therefore, the gases will be very compressible, since the space can be shrunk and have such low densities because there is space between them. Whereas in solids and liquids, there is very little space and the particles are even touching each other. So this also means that increasing pressure will reduce the volume of the gas, since the pressure will compress that space between the gas particles. Also, gases have higher pressures at higher temperatures. The kinetic molecular theory explains this by stating that the kinetic energy of a gas is directly proportional to its absolute temperature. So this means that the particles are moving faster at higher temperatures, and thereby the pressure will increase since the particles are hitting the container walls at a higher frequency. Another property explained by the theory is how lighter gases diffuse faster. So since kinetic energy is dependent on temperature, all gases must have the same average kinetic energy. Therefore, in order to have the same average kinetic energy, slower gases must weigh heavier or have higher molar masses, since this is the only way that the kinetic energy can be maintained the same throughout all gases. And then another property is that more gas particles results in a higher pressure, and the kinetic molecular theory can be applied to this to explain it, since it states that there are no intermolecular forces between the particles and gas. So this means if you add more gas particles, the presence of more gas particles will make it so the gas particles are more likely to form intermolecular forces. Therefore, the gas particles will collide. There will be more gas particles to collide with the container walls. And another property is that gases are miscible, meaning that they mix homogeneously in mixtures. So since there are no intermolecular forces, that means there's gaps in between the gas particles, where gas particles can freely mix. Moving on with Graham's law and rates of fusion, so we know that density is proportional to molar mass, and molar mass makes particles move at slower speeds. Therefore, the rate of effusion from the container will be lower than for a gas whose molar mass is a lower value. So this is Graham's law, and it's that fusion rate is inversely proportional to density and mass. So using this to compare the relative rates of fusion of two gases, we can go ahead and do this with oxygen and carbon. So we have the rate of oxygen over the rate of carbon equals the square root of the molar mass of carbon over the molar mass of oxygen. And this gives us 0.87, and this makes sense since oxygen has a greater molar mass, so it should have a lower fusion rate. Now let's go ahead and relate the root mean square speed to temperature and the mass of gas particles. So first, let's go ahead and create the foundation. So the square root of the average. So the root mean squared speed is the square root of the average of the squared speeds of all the gas particles, and this gives us that the average kinetic energy for the gas particles in temperature is the average kinetic energy is equal to 1/2 m root mean squared speed. So since we know that the average kinetic energy is the same for all gases, this means under the same temperature means that the kinetic average is also equal to 3/2 times the Boltzmann constant times temperature. So rearranging the variables, this gives us that the root mean squared speed is equal to the square root of 3 times the universal law constant times temperature all over of the molar mass. So looking at the equation, we see that the speed lowers as the molar mass increases, which we already know since the kinetic energy must stay the same for all gases, and it increases as temperature increases, which also makes sense since kinetic energy is proportional to temperature. Now let's go ahead and discuss how a manometer works to measure gas pressure. So a manometer consists of a straw-like tube connected to a mercury pool. The tube has the air sucked out to produce a vacuum, and the top is closed off. This will cause the pressure of the external gas to push the liquid up the tube, and the difference in height from before and after the gas pushes the mercury gives a measurement for the pressure of the gas, and this is usually used for calculating atmospheric pressure. We must also take into consideration that there are several units to express gas pressure. And here in the table at the right, we see the unit conversions for some of those gas pressure units. So let's go ahead and take a look at them. So 1 atm, or one atmosphere is equal to 760 milliliters of mercury. It is also equal to 760 torr. It's equal to 29.9 inches of mercury. It's equal to 14.7 pounds per square inch, which is also written down as psi, and it's also equal to 101,325 pascals. Also, for torr and millimeters of mercury, notice how it's the exact same conversion, and they're always going to be exactly the same. The only thing that changes is the abbreviation. So for millimeters of mercury, you have mmHg, and for torr, you have torr.
Now we will be discussing gas laws and relating volume, pressure, temperature, and moles. So first off, we will be talking about ideal gases. Ideal gases are particles that do not interact with each other and are dimensionless points in constant, random, straight-line motion. We are able to determine the parameters of these gases by using the gas laws. Let's discuss Aem-Seang's law. This law proportionally relates pressure and temperature. The mathematical expression for this law is P1 over T1 is equivalent to P2 over T2. We can use this expression along with the expressions for other gas laws to determine unknown parameters for gases. Then we have Avogadro's law, which relates volume with the number of moles when temperature and pressure are constant. The mathematical expression for Avogadro's law is V1 over N1 is equivalent to V2 over N2. Then, Boyle's law states that pressure and volume are inversely proportional. The expression for Boyle's law is P1 times V1 is equivalent to P2 times V2. Lastly, we have Charles' gas law, which states that volume is proportional to temperature. The mathematical expression for Charles' gas law is V1 over T1 is equivalent to V2 over T2. Now that we have examined the relationships between pressure, volume, and temperature with a fixed amount of gas, we can combine the gas laws and we get P1 times V1 over T1 is equivalent to P2 times V2 over T2. Finally, we have the ideal gas law, which differs from the combined gas law because it also establishes a relationship between moles, while the combined gas law only relates pressure, volume, and temperature. The ideal gas law is PV equals nRT, where P is pressure, V is volume, N is moles, R is the gas constant, and T is temperature. That will sum up the gas laws and relating volume, temperature, pressure, and moles.
Well, let's go ahead and move on to relating the ideal gas law to density. So we know that density is equal to molar mass over molar volume. So if we multiply a molar mass to both sides of the ideal gas law, we can get density on one side, and then we can get on the other side of the ideal gas law, we get molar mass times pressure all over the universal gas constant times temperature. And if we just plug and chug, we can go ahead and get density. So we can see from this equation that density increases with molar mass, which makes sense since you can have more gas particles. So the particles are going to be more packed together. We also see that it decreases as temperature increases. And this would happen because when temperature increases, the molecules are moving faster, so they're diffusing out faster. So the molecules can be less packed together, and the density increases with pressure. And this also makes sense because pressure is compressing the gas, so the particles are going to be closer together. So we can go ahead and apply this in an example. So the question asks, what is the density of 1 mole of oxygen at a pressure of 1 atmosphere and 30 degrees Celsius? So again, we just go ahead and plug in the values. So we have 32 grams per mole for the molar mass times 1 atmosphere all over the universal gas constant, multiplied by the temperature in Kelvin, which is 303.15, and we get the density, and for the density we get 1.32 grams per liter. Alright, so let's go ahead and move on now to relating volumes using stoichiometry. So we're going to go ahead and explain it by using an example. So our example is the combustion of methanol, and the question is asking how many liters of carbon dioxide are produced when 1 gallon, which is 453.6 grams of methanol, is burned. And we're in the situation we're given that this is happening at 1 atmosphere and 25 degrees Celsius. So the first step to relating the volumes is to transfer the grams or gallon of methanol to moles, and then the moles of methanol to moles of carbon dioxide. And then using the ideal gas law to find the volume of the carbon dioxide produced. So we're going to go ahead and do this. So we have 453.6 grams of methanol times 1 mole of methanol over the molar mass of methanol, which is 32.04 grams. And then we multiply that by the ratio of CO2 to methanol, which is 2 moles of CO2 for every 2 moles of methanol. And this gives us the moles for carbon dioxide, which is 14.16 moles. So now we can go ahead and isolate for volume in the ideal gas law, and this gives us that volume is equal to moles times the universal gas constant times temperature all over pressure. So when we plug in the values, we get 14.16 times the universal gas constant times the temperature in Kelvin, which is 298, all over 1 atmosphere, and we get 337.57 liters of carbon dioxide produced.
Now we will be discussing mole fractions, partial pressures, and the van der Waals equation. So first off, what is a mole fraction? Mole fractions are the ratio of moles of a substance in relationship to the total moles present. Mole fractions are used in the law of partial pressures, or Dalton's law, to find the partial pressures of each gas when given a total pressure and the moles of each gas. The expression for the law of partial pressures is P1 plus P2 plus however many gases you have is equivalent to the total pressure. For example, a storage tank contains 2 moles of argon, 3 moles of oxygen, and 5 moles of nitrogen at a total pressure of 1000 torr. We must calculate the partial pressure of each gas. Our first step is to find the mole fractions of each gas. For argon, we divide moles of argon by the total moles present. So we have a mole fraction of 2 over 10, or 0.2. We repeat this step for each gas that we want to find. So for O2, we get a mole fraction of 0.3, and for N2, we get 0.5. We then multiply each mole fraction for each gas by the total pressure, in this case 1000 torr. We will end up with 200 torr for argon, 300 torr for O2, and 500 torr for N2. That sums up how to use the law of partial pressures. Now onto the non-ideal behavior of gases and the van der Waals equation. Previously, we discussed using the ideal gas law to find undetermined parameters for ideal gases. However, the issue arises when we work with a non-ideal gas. Non-ideal gases can be described using the van der Waals equation. The van der Waals equation is very similar to the ideal gas law with a few additions or corrections. While the ideal gas law was PV equals nRT, in the van der Waals equation, we have P plus An squared over V squared times V minus N times B equals nRT. Like the ideal gas law, P is pressure, V is volume, N is moles, R is a gas constant, and T is temperature. However, we introduce 2 new variables, A and B. A represents a constant that describes the strength of attractions between molecules. Larger and more polar molecules have higher attraction, while smaller and less polar molecules will have a lower attraction. B is a constant that describes the size of gas particles. An squared over V squared is the attraction between gas particles. Each gas will have its own set of specific values for A and B to be used in the van der Waals equation, some of which are included in this table here. That will conclude our Chapter 9 overview. Thank you for watching.